I'm going to be talking about a literature compilation looking at the constraints that we do have and the constraints that we need regarding magma storage along the Cascade Arc. So the Cascade runs from Northern California, so Lassen Peak, all the way up through Oregon and Washington to the Garibaldi volcanic belt in Canada. And it comprises a number of iconic stratovolcanoes, so Mount Baker, Mount Rainier, Mount St. Helens, and Mount Shasta. And in addition to these large edifices, there are also a very large number of cinder cones and other mafic features between these volcanoes. And there are two main types of tools which have been used to determine magma storage conditions in the Cascades. The first is petrological methods. This includes things like melt inclusion barometry, where we use the water and carbon contents of melt inclusions to calculate the pressures under which that melt was trapped. Experimental constraints based on equilibrating natural materials and comparing them to erupted crystal chemistry. And the compositions of minerals themselves through the use of mineral melt and mineral-mineral barometry. There are then a number of geophysical methods that have been used, so geodetic constraints from tilt and insar, looking at the depths of deformation sources, as well as magnetotelluric and seismic models of the velocity and the conductivity structure of the crust. When we're looking at these volcanoes, we're going to be looking relative to their threat level. So in 2018, a national threat assessment gave each volcano a number and a ranking out of all of those volcanoes in the US. So you can see Mount St. Helens is the second most hazardous volcano in the US, and Three Sisters is the seventh most hazardous. So first, let's look at what mineral data is available. You can see it is very, very variable. So for example, Mount St. Helens has a large number of amphibole analyses, Mount Adams has a large number of clinopyroxene analyses. But there are also a number of volcanoes where we have very little data. So for example, from Mount Shasta, there is no usable mineral data from the main edifice for doing thermobarometry. For Three Sisters, we have 6 published clinopyroxene measurements from North Sister and 12 from South Sister. And for Newbury, again, no published mineral data. And this causes problems. Mineral melt barometry is not very precise, and that means you need a large number of measurements to get an average that you can rely on. And the main reason for the lack of data is simply that many studies publish just representative mineral analyses, so just 3 for a given edifice, or they weren't published at all. And those analyses have simply been lost to time. Let's look at melt inclusion data. So here we're showing the number of melt inclusions that have been measured at each volcanic center. And again, very variable. Lots from the cinder cones around Lassen, a lot from Crater Lake, but absolutely none from Mount Rainier, Three Sisters, or Mount Adams. It is also worth recognizing that almost all of these measurements just measured the glass phase of the melt inclusion. However, since about 2014 and 2015, become very clear that an awful lot of the CO2 is hosted in the vapor bubble. And from the Cascades, we only have 13 measurements where both the vapor bubble and glass was measured in a single melt inclusion. And those are all from the Lassen region. So what does this mean for the published pressures from melt inclusions? Well, simply it means that they're too shallow. So this graph is showing the calculated depth versus the CO2 content for 2 different water contents. So a relatively dry Cascade magma on the left, this might be Rainier or Baker, and a wetter one on the right, so maybe Mount Shasta. So down the bottom, you can see the histogram of measured Cascade glass CO2 contents, and most of them are below about 1,000 ppm. And the mean would result in 4 kilometers depth for 2 weight percent water and 12 kilometers depth for 6 weight percent water. Now, as you increase CO2, that pressure and therefore the depth is going to be increasing. So we measured 339 vapor bubbles from 10 different volcanic centers, and we found that the vast majority of them have some CO2 in the bubble, either as a fluid or as a carbonate, and only 50 of them had no measurable CO2 or carbonate. So we can reconstruct the CO2 content, and we can see now, instead of having about 500 ppm CO2, we have more like 3,000 to 4,000 at many of these volcanoes. And for your relatively dry system, that pushes you 5 times deeper. And even for this wet system, that pushes you twice as deep in the crust. So this means it is very hard to have any faith in the published melt inclusion saturation pressures that exist, both in the Cascades and probably other arcs globally. Let's look at a case study of Mount Shasta, one of the hazardous volcanoes. And it's very interesting that actually the vast majority of petrological studies have focused on this high magnesium andesite. This is about 5 kilometers away from the main edifice. There is no published mineral data that we can use on the main edifice and no published melt inclusions there either. So while we have quite a lot of data for this high magnesium andesite, because people are very interested in this in terms of the origin of subduction zone magmas and the interaction with the crust, it is not really telling us much about the hazards under the main edifice. And even the melt inclusions which we do have for that, they did not measure their vapor bubbles. And every single Shasta melt inclusion I have seen has a vapor bubble, and there is between 4,000 and 5,000 ppm carbon in those. So even for these side vents, we are pushing magma storage much deeper than we thought. In terms of other constraints, there are some experimental petrology constraints. The amphibole ones in particular will also be influenced by CO2 because they're assuming that the pressure they're calculating is for a pure water system. And then there is a low velocity zone that has been recognised, but only in a regional tomographic model. Shasta has seen no deformation, so it's very, very hard to use INSAR or tilt. And there haven't been any high density local seismic or magnetotelluric deployments. So to understand why we have so few constraints on magma storage, let's look at the seismic network. And you can see here, there was a reasonably small number of one component short period seismometers. These aren't super useful for getting magma storage depth. And recently we have now seen 4 3-component broadband seismometers go in. There are relatively few earthquakes at Shasta, which make using this new network to invert for magma storage still challenging. But with time, as those earthquake comes in, it is possible this new network will allow new depths to be found. The lack of seismometers is a problem at many Cascade volcanoes. So Glacier Peak has a single seismometer and it's only one component. And Mount Baker, until recently, only had 2. And even now, there's only one 3-component broadband. And this represents permitting issues in the Cascades fundamentally. The USGS has made great strides at some volcanoes. So we can see at Crater Lake, we now have 4 3-component broadbands. So again, waiting for earthquakes, but there is potential for new geophysical inversions here. And the same is true at Mount Hood, a really recent increase in 3-component broadband seismometers. So in summary, there is a lot of work to be done to understand magma storage depths in the Cascades. We need to really consider bubbles and melt inclusions and the fact that the vast majority of published data is going to be 2 to 5 times too shallow in terms of the storage depth it invokes. We need to be focusing a lot more on the main edifices in terms of mineral chemistry and melt inclusions. Most of the work has been done on cinder cones. This is important for understanding the mafic input into the arc, but isn't really telling us about where these large eruptions were stored before they came out. We need to make sure there are far more mineral analyses being properly published rather than just publishing representative analyses. This means a lot of the work that has been done is going to have to be done again. And at the moment, there are going to be continuing permitting issues in terms of doing geophysical methods. And there's a very interesting New York Times article about this, which I would recommend anyone to read. So with that, I'm happy to take any questions.